everything that we have done so far in this topic, with, I guess, the possible exception of part 4. But parts 1 to 3 will culminate today with us proving trigonometric identities. So statements will be given, statements that are apparently true, and we have to prove that the statement is, in fact, true. We have a ton of trigonometric identities at our disposal, and as a result, we can develop others and prove others. Now, when we have them, they are in this kind of format, a left side equals right side, and we have to prove that it's true for all permissible values. We don't have to worry about what those non-permissibles are. We just have to be able to prove that this works for whatever the permissible values actually are. There's a number of ways to do that, but what's very necessary is that we don't start playing with the two sides together. So we can't take something like this and say, I will multiply by cosecant x and cosecant x. So that way we get rid of this fraction-y fraction. Right? That is not something we do. We keep these sides completely separate. That there is a left side and there is a right side. And we manipulate each one until the left and right are equivalent. As we're doing so, and there's a few ways to do that. You could just stick with only manipulating the left side. That's an option. You could only manipulate the right side. That's an option too. Or you can play with both sides. And this both sides might have to happen frequently, especially if the left and right are looking rather complex. If one side is very simple looking, then perhaps we don't have to manipulate both. Generally speaking, it might be a better choice to work with a more complex side and try to make it look a bit simpler. Here we have those kind of situations, but also just spot what you can do. So what is it we could possibly do in a situation like this? What could we do to the left side? What could we do to the right side? Because again, with all the options we have for identities, there are many options for paths to explore. Some of those paths will get us stuck, and as we are doing these trig identities, we might find ourselves stuck, we might find ourselves frustrated, it's going to be annoying and irritating and irksome. But as we try the various paths, despite however many times we get lost, we will eventually find the path that leads us forward and to our destination. If you want, you can just try giving this a go. I think there's at least one thing that you can spot for this particular example. I'll just provide us a little bit of setup here. And that's to say that as we do this, we may want to, and we should, divide this into a left side and a right side. And then with that done, just carve a line right down there, although I could do a better line than that. Good enough. Questionable. So we have our left side, or left-hand side, if you will, and our right side. And we're going to work with them independently. So on my left side, I have tan x cos x divided by cosecant x. On my right side, I have 1 minus cos squared x. Again, I don't have to work with these in any particular order. I don't have to work with both of them. I could work with just one if I want. But I'm seeing what I can do and where I can go. For me personally, the first thing I see is that on the right side I've got 1 plus cos x, and maybe I can actually change that. So that's the first thing I see. So I'm just going to quickly change colors here. Make all those parts black, and I'll make this part pink. I'll just erase it, sorry. I wasn't sure which pink I used. Anyways, what I see on the right side is that I've got 1 minus cos squared x, and I know that to be the same thing as sine squared x. That's from our first Pythagorean identity. Nice. Wicked. Super. I could go and do other things with that, I suppose. But to me, I look at this and I say, well, that looks really simple. Like, I don't want to introduce any more complexity than I need to. That right side looks nice. And I would like this left side to just look just as nice. I know at this point I need to get sine involved somehow. So I'm going to keep that in mind as I do this left side. I might consider expressing tan and cosecant using the quotient and reciprocal identities. So I could say that tan of x is sine x over cos x. And I can say that cosecant is 1 over sine. Of course, keeping my variables present for the entirety of this thing. Well, on top, hey, check that out. These two will cancel each other out. And I'll just be left with sine x. On the bottom, I have 1 over sine x. If you want to rewrite that statement as this, you can. If you want to rewrite it as multiplication, you can. But what's key is that we can determine that it is eventually sine squared of x. That is a beautiful moment, because at that moment, my left side and my right side equal the exact same thing. It's wonderful. I can say that my left side and my right side are equivalent. This is a necessary statement. Look how that squiggle turned out. Therefore, what I had on the left side, which was tan x cos x over cosecant x, is equal to whatever I had on the right side, which was like 1 minus cos squared x. This thing, this proof, is done. There's this one. And again, we set up with a left side and a right side. And I'll put what I've got in each one. On the left side, I've got just tan x. And on the right side, sine of 2x over cos of 2x plus 1. Interesting. I'm looking at this left side. It's just tan x. That looks very simple, straightforward. I don't really want to do anything with that. I'm personally going to choose to leave that side alone and work just with this side. Alrighties. What could I possibly do? Well, we've got some double angles happening here, and there's no double angles on this side. So I think I would personally start with getting rid of that and using my double angle formula to say that sine of 2x is 2 sine x cos x. And cos of 2x is something. I've got options here. Right? Cos of 2x could be expressed a few ways. Whoops. You could say that it was cos squared x minus sine squared x. You could also say that it was 2 cos squared x minus 1, or that it was 1 minus 2 sine squared x. We got options. What I'm thinking is that I might want to use this one. And the reason I'm thinking of using that one is because of this plus 1 over here. I figure if I replace cos 2x with this, and that there's this plus 1 at the end, well then these are going to cancel each other out, and I won't have any plus or minus anything tagging along there. So that's the logic that's going behind this decision. It doesn't mean I have to go that way, but that's what I'm feeling. And I have a fair amount of math experience, so you can trust me a bit. Maybe, I don't know. Don't trust anyone. You can trust me. Don't trust anyone. But let's trust me. So I'm writing cos of 2x as 2 cos squared x minus 1, and then that plus 1 is still kicking around on the right side. And again, my rationale behind that was that in doing so, the ones would cancel each other out, and I'd just be left with 2 cos squared x. Oh yeah, this looks super dope. This is fantastic because my cos x's will cancel, and my 2's will cancel. And I'll just be left with sine x over cos x. And that I know is tan x. These are facts. Sometimes it might be that you don't actually see that right away. And not to encourage this, but just worth noting, you can kind of pull some shenanigans here and there and everywhere. You know that your target is eventually tan x, and you might be looking at this and being like, where on earth could I possibly go? But you know that your target's tan x, and you know that tan can be expressed as sine and cosine. So maybe you don't see this step right away, but you kind of pretend that it exists. Now do double check it, make sure it's true. But sometimes you can look at the destination to kind of figure out which way you need to go. In any case, we have that the left side equals the right side. Therefore, tan of x is equal to that other stuff. Sine of 2x all over cos of 2x plus 1. Boom. Done. It's super, it's swell, it's splendid. Now there are 2 more identities to prove on the next page. Please give them a shot. Give them a try, and like, they look intense. They look like doozies. And again, you could get frustrated, you could get stuck, and that's okay. But whenever you do, just consider what you can do in any possible circumstance. This might be a scenario where you really want to frequently involve scrap paper, just to find paths on the side. And it might be that you end up on the scrap paper with a very, very long and involved solution, but then you also see in your work that you kind of went around a particular point a few times before you found the one that worked. So work with that a bit. See what you can get. I will be going on, but I'm going on in the hopes that you have paused the video and tried these on your own. Oh, rip. Oh, close. Maybe you'll finish doing an identity in the time it takes me to draw a straight line. I'll take it. All right, my left side is this, and my right side is that. I don't have to work with one end to completion and then work with the other end to completion. I might be working with one and then I'll turn it into the other a bit. Maybe I'll look at the right side for a bit, I'll look at the left side for a bit, maybe I'll go back to the right. It doesn't matter. Again, as long as we can get the left and right side to be same. To be honest, when I'm looking at this, I'm looking at the right side and it doesn't look all that bad from what I see. I see things I can do, and that's where I'm going to go. Again, you've done this, you've tried it already, so you're just seeing if your path is the same as mine. I'm looking at this 1 minus cos squared x, and I just want to change that. So I just changed it into sine squared x. And I kind of wanted to do that because I saw sine squared x on the bottom here. And I figured, well, that's kind of a good target to have. Of course, now I see that, I'm also seeing that I can kind of cancel those 2 out. And I just have sec squared x. So that's pretty nice and simple on that side. Over on this side, what can I do? Well, we've got sec squared x minus 1. I could probably do something with that. I might need to refer to formula sheet. I think that secant relates with tan. And I'm pretty sure that secant squared x minus 1 is tan squared x. If I'm wrong, I'll know pretty heckin' quick, because this will just become a mess. Well, it looks like it's becoming simpler. So there's that. Tan squared x is sine squared x all over cos squared x. Which means that I have just 1 over cos squared x. If you want to work out that complex fractions division, feel free, but that's how it works out. And 1 over cosine x is secant x, so 1 over cos squared will give me secant squared. Left side equals right side. And I can say that those two sides are then equivalent. I can say that, therefore, sec squared x minus 1 over sine squared x is equal to, whoopsie daisies, sine squared x sec squared x all over 1 minus cos squared x. Wicked. And the last example is that one. My left side is 1 over 1 plus sine x. My right side is sec x minus sine x sec x all over cos x. We've got ourselves a doozy on our hands. Now the left side doesn't look too bad. It doesn't look like there's much involved, but to be honest, that's something that we will still probably want to work with. Whenever I see 1 plus a function or 1 minus a function, and there's no like squared involved up here, I'm thinking to myself, I'm probably going to want to multiply by the conjugate, because I'm going to have then 1 minus something squared, which might relate to a Pythagorean identity. So that's what I'm thinking in that case. And that's what I'm going to go with. So styling this one is bleh. I'm going to take this one, I'm going to multiply top and bottom by 1 minus sine x. It's a sneaky technique, but it's one you should familiarize yourself with, because it can be useful. With that, like the top of it doesn't look the best, and it doesn't look simpler than I originally had, but I like that the denominator is a bit nicer to look at. So there's that. On the other side, whew, interesting. So I'm just looking at my target. There's a ton of things we can do. We can convert the secant into a 1 over cos if we want. I'm not sure really what else we can do. But I'm going to sneak attack this. I know that I want a cos squared x in the bottom. And I know that right now I've got a regular cos x. So, part of me is I just change the color there. The same? Nice. So I'm thinking maybe I just multiply top and bottom by cos x. Because that'll give me the denominator I need, right? That's going to give me this cos squared x on the bottom. And then hopefully the top works out to the same top here. So we've got secant x cos x minus sine x secant x cos x. I see what I see. If you look at something like secant x times cos x, knowing that secant of x is 1 over cos of x, and that we're multiplying it by cos of x, means that this is really just 1, and this is really just 1. Oh, sick! This is wicked! Math is the best! So we could go in here. Where's my pink? I found it. Sec x times cos x is 1, and then sine x times sec x times cos x is sine x times 1. So that's just sine x. My denominator is same. Oh man, look at that! Left and right side. I don't know about you, but I think those look pretty similar. Therefore, I can make one heck of a declaration. I can say that the left side is equal to the right side. And therefore, 1 over 1 plus sine x is equal to sec x minus sine x sec x over cos x. And that's done. Did I proof done that one? Whew, what a doozy. And it is a challenge. You don't necessarily see all these things right away. And that's okay. But as you practice them more, you'll start to see these things more often. While you'll still see the multitude of paths that are there as options for how to proceed, you'll start getting a bit more of a sense of which ones are the better ones to take. And you've taken those trails before, and you know where they lead. So, oh my gosh, there's still another one? Thought it was over. Fine, let's do this. Hopefully you tried it. Try it now. I'm diving in. Oof. Okay. My left side is sine of 2x minus cos x all over 4 sine squared x minus 1. My right side is this. Yuck. But I know what I can do. On the right side, at least, I'm seeing a common factor of cos x. So I think that's sine squared x plus cos squared x is 1. So that's that. I don't think I want to go any further than that with that one. But I've got my target set now. Sine of 2x, I'll rewrite that as 2 sine x cos x. And I'm thinking I probably want to factor this. Yeah, difference of squares, I want to factor that because one of the factors will be the same as this denominator here. So 2 sine x plus 1, 2 sine x minus 1. Nice. Erase that. So then on top I've got that cos x common factor. Yes, this is the way. And then these two things can cancel each other out, which means I've just got that. Yes. So my left and right sides are equal. Therefore, this expression on the left must be equal to this expression on the right. And this one is done. Hooah! Now we're done all the examples. Thank goodness. That was a doozy. So just remember, we will never work with both sides at the same time, so they're treated independently. We have the left side, we have the right side, things don't transfer over. And there is a ton of identities we can use at any time. And we need some practice and maybe some foresight, following some ideas that we get from a sense of having done these before to help us decide which way to go forward. And scrap paper is super helpful. You might get stuck, you might be erasing 400 times. You might find the right way to go first try, who knows? But I would say complete the proof on a separate page and then transfer it over. Practice-wise, here's a bunch of practice questions. So play with those. Please let me know if you have any questions, comments, concerns. And of course, this does mean that we are at the end of this topic. So there's some textbook review for you there. And then from the previous, or from the 2019 provincial, we've got these 3 questions to look at. You can pretty much always expect there to be one identity, and you can always expect there to be one k pi over 12 kind of question. So that's that. It's been a great topic. I look forward to seeing you in our next topic, which will be trigonometry again. But it's our last trig topic. That one, topic 9, will be the last one. I swear. I promise, I swear. And that's all. Goodbye!